Let's see.
This is the thing where you don't want to play the same time. You have to turn your head. There's close that to your gut. Because at the end of that, you gotta use the whole thing.
All right. Let's see here. If we can turn to page 9.
Yeah.
We haven't done 14 yet, have we? No. Okay. All right. So let's go ahead and try 14. Understand that I think sometimes students get a little bit thrown off when there's multiple variable or constants that's represented as A or B. So we just want to treat B like we would if it was like a 2 or 3 or 5. Okay, so just keep that in mind. Okay, so first thing we do is we go ahead and evaluate our limits. We don't know what's going on there, so we want to gather information. So if I replace all the x's with b's, what do we get? 0 over what? Yeah, 0 over 0. So we know it's indeterminate form. We know there's a hole. That hole indicates that the limit does exist. We just haven't found it yet. So we look at how this problem is set up. Looks like the radical can be handled using conjugate methods. So multiply the numerator denominator by conjugate of the denominator. And the hope is to get that denominator to be a little cleaner so we can get that to match with something in the numerator that we can then cancel out. Okay. All right, so try that, see if you can work through those steps, and then we'll compare our work. Right, so we do want to FOIL out the denominator, but the numerator leave alone, because that b minus x in the numerator is ready for us to match and pair up. Oh, I just thought of this in terms, students was asking about this in terms of notation. So typically, we're supposed to hold on to our limit notation until the variable is gone. Once we plug in, once we make our substitution into your variable, then the limit notation is no longer required. But technically, limit notation needs to be rewritten as long as your variable is still in play. Okay. But on your homework or on the test or assessment, If you really don't want to write it every time, you can just draw an arrow just to indicate to me that you know that the limit notation is supposed to be there. And then as soon as you do direct substitution that leads to your answer, then your limit notation is no longer needed. All right, so the denominator cleans up nicely because of the conjugate. Multiplied by the conjugate here, we're left with just x minus b. Now x minus b is close to being the pairing up with b minus x. We can cancel these out. We just have to make sure we hold on to a what? A -1, right? So once that -1 is accounted for, you can then do direct substitution, replace the remaining x's with b, and we should be left with something other than 0 over 0. So -2 root b. Okay, let me walk through 15 with you here. Okay, 15, it says use the piecewise functions to find the given values. So here we have limit as x approaches 2 from the left side of 2. So that means we want to identify which piecewise function is living to the left of 2, moving towards 2, and we want to use that. Right. So which piecewise function can we use then for the second one, right? Because -2 to the left of 2, that's like, imagine like 1.9, right? Where's 1.9 going to live? 1.9 is going to live in this interval. So we can evaluate the limit here. Now, we haven't quite talked about this, but whenever you want to evaluate a limit, go ahead and if you see a one-side limit there, ignore it to begin with, okay? Just work with the integer value. We are going to, next section, we are going to see, when do we have to do something with that notation numerically, but for now, just know that it's just the real number, okay? For right now, just know that that negative will place us in the correct location, but when we do evaluation, it is just that integer value, okay? Not a decimal value, okay? So if I evaluate it with that second expression here, 2 squared minus 5, 4 minus 5 is -1. Okay, so see if you guys can do the rest of this, A through H. Okay, let me first start off by pointing out f. The limit as x approaches 2, the reason why this is able to exist is because, now if you look, this piecewise function is split on either side of 2 with two different functions defined leading up to 2 from either side. So if we want to find the limit at 2, these have to be in agreement, right? And because these are in agreement, a and e, that's how we know that the true limit does exist at 2. We only have to worry about having to work with one side of limit. It is if we have two different functions that's split on either side. If it's an endpoint of between two piecewise, right? But if 2 lands in between an expression, then we can just use that one function. There's no need to involve two expressions. But what do you notice about part G here? The limit as x approaches -4. That's good. Doesn't exist because we see that -4 is split between the first, what's the endpoint and the beginning point of two different piecewise functions of the first two. So I have information that helped me gather the fact that my true limit doesn't exist, because if we're approaching -4 from the left, I'm getting a value. If I'm approaching -4 from the right, I'm getting a different value. These are not in agreement. So therefore, the graph is disconnected. The fact that they're disconnected and moving to different y values, that indicates that the limit doesn't exist. Okay, number 16 is kind of like a special case. So let me walk through 16. Everybody good with 15? So 16, if we try to go through our normal process, right? Try to plug in 2 and we'll get 0 over 0. The x minus 2 and x minus 2, they look the same, but we know there's something that we got to worry about with that absolute value, right? And so we can't just quite cancel these out like we normally would with a rational function. But it's not asking for the true limit, right? It's only asking for the approach from the left side of 2. So in this case, I think the fastest way is just to choose a value that is relatively close to 2, like 1.9, right? I know that 1.9 is going to be close enough to 2 for me to get a pretty good read on what's going to happen. So if I insert 1.9 in for x, let's see what happens here. Absolute value of 1.9 minus 2, what is that going to give me? Yeah, 0.1, right? Normally it's negative 0.1, but that absolute value is going to force that negative to be positive. The denominator is going to give me negative 0.1, and that's equal to what? -1. All right, so that is going to be the one-sided limit as x approaches 2 from the left. And now, obviously, if we had the graph in front of us, it'll be a lot easier to identify the approach, but this is kind of like a quick workaround, especially if it's cumbersome with the absolute value. So the graph actually looks something like this. So the approach is 2 from the left. It's going to be the graph actually looks like this, right? So as we approach 2 from the left side of 2, it's going to hold steady at -1. But as soon as it moves to the right of 2, it's going to jump up to this y value of 1. All right, next page. Continuity, types of discontinuity, and intermediate value theorem. Okay, so continuity, a continuous function is if you can sketch the entirety of the graph without having to lift up your pen or pencil at any point. So here, this is a nice continuous graph here. This, however, there's no way for me to sketch this graph without having to lift up my pencil if I want to complete this graph. So anytime I have to lift up my pen or pencil to continue with my graph, we know that's going to be a discontinuous function. Okay, so there's different types of discontinuity. The first type is where there's just a hole in the graph, okay, where basically if I just do a quick substitution, if I just replace a point in for that hole, if I can all of a sudden, if I'm only one step away from creating a continuous function, then we call that a removable discontinuity. That's basically where I have a hole in the graph. Now, if I'm discontinuous due to vertical asymptotes, like this one here, okay, we call that a non-removable discontinuity. Due to a vertical asymptote. And then we also have another non-removable, that's a third instance here where it's like a jump discontinuity, where you have a piecewise function and then you're jumping to another branch, but it's not due to vertical asymptote, even though we consider both of these as non-removable. We also call this jump discontinuity. Let's see. Let me see if I can answer that question. So I'm interpreting as if it's asking for the limits at these discontinuities, we would say the limit doesn't exist. But if it's asking for a one-sided limit at for these functions, then we have to give an answer.
Okay.
Yeah. So the answers do exist for one-sided limit for these discontinuous functions, but the true limit would not exist at these discontinuities. Okay, for each function, identify the type of each discontinuity and where it is located. So if we can factor everything out, and if we can identify a location where vertical asymptote exists, we know that it's going to be a non-removable discontinuity. If we can identify a hole in the graph, we know that is a location where jump discontinuity occurs. Okay, so let's go ahead and just factor everything that we see here. Multiplies to be 12, adds it to be -8. Multiplies to be -10, adds it to be 3. So anytime where factors cancel between numerator and denominator, that's an indication where a hole exists. And if there's a hole, we know that this must be part of a removable discontinuity. Anything in the denominator that does not cancel out is going to be your vertical asymptote. And because we know there's a vertical asymptote at x equals -5, we know that is non-removable discontinuity. Okay, so this is not relevant for this problem, but I just want to ask you here, what is this x minus 6 going to give us on the graph? Here. Yeah, an x-intercept. Yeah, so that's the location of the x-intercept, just to kind of round out the behavior of a rational function. Anything that cancels out is going to be a whole. Any denominator that's left over is a vertical asymptote. Any numerator that's left over is a 0 or an x-intercept. It's a point that you can easily plot on the graph. Okay, try number 2, see if you can identify those discontinuities and where they are. Okay, just keep in mind that difference of squares you can factor, but sum of squares you can't factor. Okay, so if I have x squared plus 4, that stays. I can't do anything with it unless I involve imaginary numbers, but we're not working with imaginary numbers in this course. Okay, so my denominator, I can do a couple of steps involving factoring. X to the 4th minus 1, I can break them down into x squared minus 1 and x squared plus 1. And go a little further with the x squared minus 1. That's also a difference of perfect squares, so x minus 1, x plus 1. But the x squared plus 1 stays. I can't do anything with it. I do have a hole at x equals -1. I do have a vertical asymptote at x equals 1. But the x squared plus 1 is not going to produce anything. If I try to set that equal to 0, I'll get an imaginary unit. So nothing will come from that. Or there's no discontinuities that's going to be produced from that x squared plus 1. Okay, next, we know what a continuous function looks like, right? We know that visually, if we can imagine ourselves sketching the entire graph without having to lift our pen or pencil, that function is continuous. But then how do we formally define it if we only had a function expression to work with and we don't have the graph in front of us? Okay, so this is the formal definition of continuity involving ordered pairs and limits. Okay, so in order for a function to be continuous at a specific point, now this definition of continuity is only proving if a function is continuous at a point. Okay, it's not going to be able to, if we want to figure out continuity at various points, we got to do it various times. So this is only continuity, defining continuity at a single point. So in order for a function to be continuous at a specific point, x equals c, and that if they're asking if a function is continuous, they always have to provide you a target point to work with. Okay, so that's always going to be given. Okay, now the following 3 conditions must be met. The first is that the point has to be defined, right? We can't, let's just start with the most basic, right? I can't have a continuous function if that point is not even defined. So first, I need to make sure the point is defined. So just simply plug c into the function and see if it exists. Okay. And the second condition is, does the limit exist? So in order for the limit to exist, we just want to know, does the graph connect and move towards the same y value? So if it's just one function, then that's great. I can just find the limit of that function. But if it's a piecewise, if it's a piecewise function, and I'm split between both sides of that piecewise function, then I would have to maybe explore a little further and find the one-sided limits and see if they are in agreement, just like how we did the previous example. And see if they are in agreement. If they are, then great, then it will pass the second condition. Now, in order for the third condition to work, the third condition just basically says, look at what you gather from 1 and 2. Are they in agreement? Is the point that's defined, is that located in the same place as where your limit is defined? In this case, I purposely drew it where the point did not match up where the hole is. So this would fail the third condition, even though it passed the first two. So in order for the third condition to pass, that point has to be in the exact same location as where you found your limit to be. Right. So this one would be a removable discontinuity. At x equals c, since the limit as x approaches c of f of x does not equal to f of c. Okay, so I'm just working a quick example of when, how to phrase it or how to justify your answer if it does not pass that third condition. Okay, so let's do number 1 and see if we can practice going through each of the conditions as we work through this problem. Okay. So sorry if I did not provide you ample space to do all your work, but let's see if we can squeeze this in. So number 1, it says we have a piecewise function, right? 3 separate branches, all with various locations defined. State whether the function is continuous at a specific x value. So justify your answer. So -1 is our target. We want to know, will it pass through all 3 conditions? And we're doing this because we don't have the graph in front of us. Obviously, we can graph this out, we can see it, but we're asked to justify using continuity conditions. So the first step is just finding the point. Okay, so let's just find a place to plug in -1, do direct substitution. So where can I insert -1? Right, the second one, right? It's not defined at the first one is close, but it's defined at -1 for the second piecewise. So insert -1 in for that second piecewise. I get -1 plus 2, which is 1. Okay, so we're good there. Keep going. Second condition. Does the full limit exist at -1? Now, is there just one function I can plug into to involve the limit here? Notice that I have different graphs on either side of -1. So -1 is the endpoint of 2 different graphs. If that's the case, I need 2 separate limit statements. If I need 2 separate limit statements, I need to do one side limit, 1 for each. Okay. So I need to do a limit as x approaches 1 from the left side of 1 for that appropriate function, and then limit as x approaches 1 from the right side of 1 for the other appropriate function. And then we basically have to do those calculations separately and then see if they line up. If they line up, great. We can check off the second condition. We can move to the third. Sorry, approaching -1 from the left. So approaching -1 from the left, that's the x squared minus 2x plus 1. From the right is the x plus 2. So if I insert 1 into the first piecewise function, I'll get 1 minus 2, sorry, 1 plus 2, because the 2 negatives cancel out. So 1 plus 2 is 3, 3 plus 1 is 4. But from the other side, the graph is headed towards 1. What do you notice? Not in agreement, right? My limit, my one-side limits are not even headed towards the same y value. So therefore, my function is not continuous because it fails that second condition. Okay, any questions? So because the one-sided limits are not in agreement, I know I can conclude that my full limit does not exist. And if my limit doesn't exist, it's a jump discontinuity, which I can categorize as a non-removable discontinuity at x equals -1. Okay, part B. Step through your continuity conditions one by one and see if you can decide on the appropriate conclusion, right? It's either one of three things. It's either going to pass through all conditions, which means the function is continuous at x equals 2. The second option is that it would fail the second condition, which means that it's a non-removable discontinuity, just like we saw here. But if it passes the first one, the second one, and fails the third one, it's going to be a removable discontinuity at x equals 2 because the second and first conditions are not in agreement. The whole and the order pair are not lined up. Okay, what do we get for part B? Continuous, okay? So, but make sure that you have all the appropriate work where you are demonstrating you're using the specific language specified in the continuity condition. So first, you plug in your order pair, get that order pair. Second, you realize that there is a split of piecewise functions at 2. So I need to look at the limit from the left side of 2. I need to look at the limit from the right side of 2. They are defined by separate piecewise functions, but they both produce the same y value. So because the one-side limits are in agreement, you know you can conclude that the true limit does exist at 4. And then the third condition, you're just stepping back and looking at your first two conditions, see what conclusions you have, and see if they are in agreement. Okay. Now, I want you to say more than since 4 is equal to 4, f of x is continuous. I want you to use this language in here and actually spell out that third condition and say, since the limit as x approaches 2 of f of x is equal to f of 2, then the function is continuous. Okay, so don't just say since 4 is equal to 4. I want to College Board is also looking for that specific language, just like how you see it in the continuity conditions. Okay. All right, let's look at some variations of continuity conditions here. I'm going to skip number 1. And let's look at number 2. Or we can just, I think we talked about this here, but yeah, so number, page 11 is just recall that if my limit exists, but my limit does not equal to f of c, basically if it fails the third condition, we know it's going to be removed with this continuity. Now, we only look at the third condition if it passes the second, right? If it fails the second one, we don't go to the third one. If it fails the second one, we stop because we already know everything that we need to know. And we only go to the third condition if it passes the second one. Now, I do want to point something out here is that if for some reason your first condition fails, if the point doesn't exist, we know it's not continuous, but we continue with the conditions because we don't know which category it's going to fall under yet. Okay, so even if it fails first, second one, right? Because even though with the first condition, if the point doesn't exist, we already know the function is not continuous, but we still don't know what type of discontinuity it is. So if it fails the first one, we still go to the second one. But if it fails the second one, we stop because we know everything we need to find. Okay. All right, so let's look at number 2 here. Number 2 says if a function is continuous, but this function is not defined at x equals -4, then f of -4 must be equal to what? So basically it's saying there's a hole here. Let's find out where the hole is. If we can figure out where the hole is, then we can figure out how to patch up that hole. But I think the easy way to do this is let's just all do the same thing every time, right? Anything that's dealing with continuity conditions, if you just step through continuity conditions, it gives you a nice structure to work through. You never have to worry about, wait, should I do this or that? If you just always go through continuity conditions, your answer will just pop up right in front of you. Okay, so we don't know what f of -4 is. So let's just do that, right? So first condition, I want to find the point, but I don't know what the point is, so I'm going to keep going. All right, first condition doesn't pass, but that's okay, which is we'll continue to gather information. Second condition is finding the limit. Now, the nice thing here is it's not a piecewise function per se, because it's only one function. This function is defined to the left of -4. It's also the same function defined to the right of -4. So we just have to do a one limit statement because there's only one function involved here. So this goes back to yesterday, right? We have to go through our algebraic steps to find the limit. What's our first step? But before that. Good, yeah, direct substitution, right? So I know we expect certain things, right? We assume that's going to be 0 over 0, which may be true, but you want to show it, okay? And then if it's a limit problem that is on the College Board, on the IP exam, they want to see your justification before you jump into further work. Okay, so we do get 0 over 0, right? So 16 minus 24 plus 8. Now we can begin working on our expression. Okay, just like what we expected, there is something that's causing that hole. We remove the hole. What's our limit? -2, okay. Good, so we made it past the second condition. And so it's basically saying, okay, in order for my third condition to work, these two have to be in agreement. So I'm going to force a continuity. So the way I can force continuity is if f of -4 is equal to -2. And just by going through continuity condition, you're just going to naturally come up towards your answer without having to do anything additional. Okay, number 3, let the function be defined by a piecewise function for what value of a is f continuous at x equals 6. We don't have to worry about, wait, how do I solve for a? Just step through continuity condition, and then before you know it, your answer will just pop up without you even looking for a. So step through continuity conditions. First condition, does the point exist? F of 6 is equal to what? A. That's all we know. Okay, so we'll just hold on to that and keep going. The second condition is the limit exists. Now, this looks like a piecewise, or I mean, in a sense, it is a piecewise function, but it's not a piecewise function that we would normally associate with one-sided limits. And the reason why is because that x doesn't equal 6 is the same graph on either side of 6. It's not less than 6 and greater than 6. Okay, so I think in the past I've had students, wonder, why don't I do left of 6 and right of 6 and use these two? And the reason why is this. Another way to think of this function is if I write it out this way. When I say x doesn't equal to 6, what that means is that this function is to the left of 6, and it's the same function defined to the right of 6. So if you want, you could do a one-side limit to the left of 6 with this function, and the one-side limit to the right of 6 with this function, but you're dealing with the same function, so you're kind of doing some duplicate work that you don't need to, right? So if you see that doesn't equal to 6, just understand that, okay, yes, I can do a one-side limit, but it's the same function on either side, so just need to do it once. Okay, there's no need for one-side limit unless you see a less than or greater than, because this is where the connected graph is. This is just a point. The point has no say as to what the limit is, so there's no need to do one-side limit if you see this notation. Just do a full limit statement, and that'll get you where you need to go. Okay, we do get 0 over 0. We continue factoring, reduce, reevaluate, and what do we get? Got to write out my limit notation here. Reduce, reevaluate. What's my limit? Fine. And then the third condition, I'm just going to look at my first two. In order for my limit to exist, my first and second condition have to be in agreement. And without even trying, you already solve for a, right? A equals what? It's 9. Okay, we didn't quite get to IVT and squeeze theorem. So if it shows up in your homework, then just try your best. But we'll go through those notes tomorrow. And then if we have time, we can also do infinite limits and limits at infinity. All right, come get your phones. Yes.
Still about
You don't have to. Because for a problem like this, it doesn't require that work. I see students in the past, they're like, they get. Filter found information, and they don't worry about doing. Don't show your steps, look at the right answers.
Not be a randomly chosen.
Running a second.
Right, so.
Oh, yeah.
Yeah, I know. There are three credit, they're probably my company, like, I guess they're.
It is now in the bell ring, please go to your advisement, and the 10th grade class will be going to them. The 9th grade class will be going to the auditorium.
No, good. Yeah. That's fine.
Thank you.
One that like was okay.
So. It's like. So I can split this up. As, I know that hospitality is like. Or. Big captions. Right, so just silly. It doesn't look. If I make an adjustment.
Okay, you should get a night. Yeah.
Transform this into these ones. Yes, Ava? Oh, sorry, Ava 10, sorry, my bad. Yeah. So you see how this, what is that reduced? This is the first one. This reduced to be negative. I get reaction, just like.
Now I just get up.
Okay, good. I said he was only going to show us twice, so that's. You're gonna only show this. He loves this. Yeah, he said he loves this, but like, there's less than 20 people. It's like, I wish I had.
Have a great day, guys. Yeah.